In this video, I'll be talking about level sensing. And when we talk about level sensing, what we're trying to do is not measure whether we're level or not, like we would with a spirit level or something, but we're talking about trying to measure the level of something within a container. For example, a liquid within a container. Now, it could be a liquid, it could be a powder or something like that, but ultimately we want to be able to measure something that won't create a little pyramid structure. We call this the angle of repose, but will flatten out. If we've got this little pyramid structure, it's difficult to ascertain correctly what the level is going to be. But if it's more liquid-like or a powder that flattens out, we can get a more accurate determination of what the level is using the level sensors that we're talking about here. So we've got plenty of different applications for level sensors. Everything from a water tank and working out how much water we've got, to a fuel tank and working out how much fuel you've got, and you see that on your little petrol gauge all the time. You've got things like grain in the silo, which may have a bit of an angle of repose to it. You might have chemicals in some sort of a containment vessel, or sometimes these level sensors are used within sewers to look at, in high rainfall events, what level of sewage comes up within those sewers and how much they increase there. And they can be used to set alarms for there might be part of the sewer that's blocked and starting to back up, and we can start identifying where that is with these level sensors. We might be sensing level as in our coolant levels in our vehicle or something, or also we might be using them in beverage and food manufacturing, pharmaceutical manufacturing, and many other related areas where we're trying to build things and we need to know how much of a particular chemical we have available. Now, there's lots of different types of level sensors, and we'll look at a few of these different types of level sensors, but we can classify these as direct level sensors, where we're directly measuring the level, indirect level sensors, where we're inferring the level based on something else. We won't focus on these as much, but in pressurized vessels, you could use a pressure sensor, for example, to look at the relative pressure between the various things like water and air within our system. And also single point level sensors, where rather than if we've got a vessel and we want to measure exactly how much water or materials in that vessel, measuring it at one point to check, oh, we've gotten up to this particular point and we know we're at that point, or down here, for example, to know that that vessel's almost empty. So they're the sort of types of level sensors we're looking at. But let's look at the ways that we can actually implement these. Well, one of the simplest would be a sight glass level sensor. Now, this isn't something that we really instrument with our sensors and computers and things like that, but we can use our eyes for it. And essentially, as the level of the material, the liquid or fluid inside our vessel rises, the level on the gauge of this sight glass rises, and we can actually see it going up. These are often marked as graduated gauges, so we can actually say, oh, well, there's this many liters, for example. And so these give us a visual indication of the amount of level of fluid within our device. Now, these can be a bit fragile. They're glass, so they can be a bit sensitive. And so it's something you wouldn't really use for corrosive substances, for example, because it might eat away at them long term. And as I already said, these give a visual indication of level, rather than an indication that will instrument somehow. Now, within our engine, we've got something called a dipstick, where we dip the stick in and we can pull it out and we can look at that and measure the amount of engine oil within our engine. Likewise, with our coolant, there's something similar. And so these sight glass style level sensors, they can be a glass, but you can have measuring sticks and things for very rudimentary methods of level sensing. Our next type of level sensors are float sensors. And basically we've got a float, something that's buoyant, that sits on top of our liquid or fluid that's within our vessel that we're trying to measure. And basically as the liquid or fluid goes down in level, the float will go down, and as it goes up, the float will go up correspondingly. Now, these can be of an entirely mechanical nature. If you take the lid off your toilet, you'll see within the system there's often a float sensor that detects whether your water's come up to the right level, and at that point it stops the incoming water from coming into your toilet and filling it up. So that's a completely mechanical approach that uses this float sensor to shut it off. Likewise, these are sometimes used on farms and things when farmers want to keep some water troughs filled up, and if the level gets too low, the float sensor opens, water can run in and fill it up, and as the level rises, it'll cut off the water flow and stop it there so the troughs won't overflow. These float sensors can also be used electrically. For example, we can put a small magnetic sensor like a reed switch and a magnet there so that when the float sensor rises, the magnet comes in contact with that reed switch and closes it and gives us an indication that our float sensor's risen. We can also do these proportionally as well, rather than just an on-off style flow switch. And so here's some examples of some of those. You can have a float switch, for example, on a water tank. You can put it over a pulley and have a little scale that you can read along. Based on the height of that float switch, your marker on the scale will be at a different height. Likewise, if we mount it on an angular rotational arm, we can work out what that angle of rotation is and how that corresponds to the level within our particular vessel. It could be something like a fuel tank, for example. And so we can instrument these electrically to work out not just where there's liquid or not liquid, but how much liquid we have within there. Now, float switches can be quite robust because you've basically got this mechanical thing sitting on top of the liquid, and they can be sealed so your electronics is kept safe. Our next type of sensor is a capacitance level sensor. And basically in our capacitance level sensor, we want to measure the change in capacitance between two bits of metal. We know classically in a capacitor, we're trying to store an electric charge between two bits of metal with a material which we call a dielectric in between them. Now, every material has a dielectric constant associated with it. Air, for example, has a dielectric constant of 1. And other materials will have a dielectric constant typically larger than this. Well, what we have is we have two probes. We might have two separate pieces of metal, or we might have one piece of metal with another piece of metal that goes around it with an air gap in between them. Or we might use one probe, and if our tank, for example, is metal, we could use the side of the tank as one of those probes. And we want to look at the change in capacitance we get with different levels of liquid that are in our system. Now, what we need in this circumstance is we need to know the temperature, because often the dielectric constant will change with temperature. And we also need to know what material, what liquid we've got within our water tank. If we know those things, we can then work out what our ratio between that liquid and the air in our water tank is, or in our tank is, and work out capacitively, based on that capacitance we're reading, what our level is. Now, our dielectric constant is basically a measure of how effectively our material can store an electric charge. And so this will work well if we know what our dielectric constant for the material is. Now, this will work well if we know what the dielectric constant for the fluid that we're trying to measure is. But if our fluid's heavily contaminated, or we've got different things in here, maybe we don't know the relative constituencies of them, it might be difficult to determine what our dielectric constant actually is. We might need to measure that separately. Our next type of level sensor is an ultrasonic rangefinder level sensor. And previously we've looked at ultrasonic rangefinders when we were doing rangefinders. And this is very similar. We basically, on the roof of our vessel that we're trying to measure the level of, we put a rangefinder there. We create an ultrasonic sound and we bounce that off the surface of what we're trying to measure, the fluid or the powder that we're trying to measure. That bounces back and we measure the time of flight from that signal to go down and bounce back. We measure the time until we receive that echo. Based on that, and based on the speed of sound, approximately 343 meters per second, and the temperature that that's taken at, we can work out what our level is for this containment vessel. Now, this has some advantages because it doesn't really matter what our dielectric constant is, like for our previous capacitive sensors where it did matter. But at times, these sort of sensors may be unsuitable. For example, if we're trying to measure through a pipe that has bends and things in it, well, the very first bend that we get to, we're going to have obstructions in there which echo, which bounce back the ultrasonic signal. Likewise, if we've got some spider webs and things starting to grow over these, or there's other obstructions that are in the way, they may bounce back our ultrasonic signals and not give us a true indication of what our level is. Our final level sensor, and I should say the final one we're looking at, because there's lots of different level sensors, some using radiation and X-rays and things. There's a whole variety of level sensors out there. But our final one that is our direct type of level sensor that we're going to look at is a radar-based level sensor. Essentially, radar-based level sensors, similar to the ultrasonic ones, but here we're bouncing radar or electromagnetic waves rather than sound waves off our surface of the level and receiving them back. Once again, using time of flight to measure how long they've taken to traverse that distance. Now, these are typically fully sealed. There's just an antenna at the bottom of them. And so they're well suited to harsh environments, but they're also quite expensive, typically a lot more expensive than our ultrasonic rangefinders that we looked at previously.